This lecture discusses confidence intervals for one population mean when the population standard deviation sigma is unknown. When the population standard deviation sigma is known, we know how to construct a confidence interval. However, in practice, sigma is usually unknown. How can we construct a confidence interval in this scenario? A natural idea is to replace the population standard deviation sigma by the sample standard deviation. Yes, it works, but it is not enough. We need to further adjust the alpha. Just recall why we have the alpha here. The sample mean x bar follows a normal distribution. In order to get confidence interval, we standardize x bar to get the corresponding z-score. Because z-score follows a standard normal distribution, we determine the value of the alpha. Now the question becomes, after replacing sigma by the sample standard deviation, is this quantity still a normal distribution? The answer is no. Suppose that a variable x of a population is normally distributed with mean mu. Then, for samples of size n, the variable t equals x bar minus mu over s divided by square root n has the t distribution with n minus 1 degrees of freedom. It is a new distribution different from normal. Sometimes t distribution is also called the student's t distribution. It has one parameter, called degrees of freedom. The number of degrees of freedom is an important concept. When we use a t distribution, we need to be careful what the number of degrees of freedom is. It is the first time that we use a t distribution. We will use it later in different scenarios. This plot shows some t-curves for different degrees of freedom along with the standard normal curve. We can see that the t-curves look like the standard normal curve, but with some differences. It is slightly lower in the center and slightly larger on both tails. In fact, when the number of degrees of freedom increases, the t-curves becomes more and more closer to the standard normal curve. This slide also summarizes some properties of t-curves. The total area under a t-curve equals 1. This is a property for all continuous random variable. A t-curve extends indefinitely in both directions, approaching but never touching the horizontal axis. It means that the density function is always positive. A t-curve is symmetric about 0. Similar to the alpha, we can define t alpha. For example, t.05 means that the area to the right is 0.05. We can use a t-table to find t-values. Different rows in a t-table indicate different degrees of freedom. Different columns indicate different values of alpha. To get t.05 with 13 degrees of freedom, we need to look for rows corresponding to 13 and columns corresponding to 0.05. The value is 1.771. Therefore, t.05 equals 1.771. The area larger than 1.771 is 0.05. You can use the t-table in the textbook. You can also use my table. My table is available on Canvas. It is also available at the following link. In my table, I mark the value of alpha as a fraction of 0.05. For example, when the number of degrees of freedom is 13, t.05 is 1.771. For t.025, Just look at the column corresponding to 0.05 over 2. The value is 2.160. For t 0.005, just look at the column corresponding to 0.05 over 10. The value is 3.012. We can also use the Excel function t.inv to find t alpha. This function has two arguments. For example, for t 0.05 with 13 degrees of freedom, we use t.inv 0.95, 13. Notice that when using this function, the first argument is not alpha, but 1 minus alpha. The input should be the area to the left. The second argument is the number of degrees of freedom. This slide summarizes the one mean t interval procedure. We assume simple random sample, normality, and the population standard deviation sigma is unknown. The discussion before on the normality also applies here. For example, we need to be careful about outliers. Follow the steps to construct a 100 1 minus alpha % confidence interval for mean. Firstly, we need to find t alpha over 2. Notice that the degrees of freedom is n minus 1, where n is the sample size. The confidence interval for mu is therefore x bar plus minus t alpha over 2 times s over square root n. Last, make sure to interpret the confidence interval. The confidence interval is exact for normal populations and approximately correct for large samples for non-normal populations. For non-normal data, as long as the sample size is large enough, by central limit theorem, the sample mean still follows a normal distribution. In this case, the t procedure still approximately holds. Let's look at one example. A simple random sample of pickpocket offenses yields the losses in dollars shown below. Use the data to find a 95% confidence interval for the mean loss, mu, of all pickpocket offenses. In this problem, we need to construct a confidence interval for mean. The problem only gives us the data. The population standard deviation is unknown. The sample size is n equals 25. The sample size is moderate. We still need to check normality. For the normal probability plot, we can see that most of points roughly fall on a straight line. Therefore, normality assumption holds. We can use the one mean t interval procedure. We first calculate the sample mean and the sample standard deviation. X bar equals 513.32. S equals 262.23. First, we need to find t alpha over 2. For a 95% confidence interval, alpha equals 0.05. The number of degrees of freedom is n minus 1 equals 24. Therefore, t alpha over 2 equals t 0.025 equals 2.064. The 95% confidence interval is therefore x bar plus minus t alpha over 2 times s over square root n. When we choose plus, we get 621.57. When we choose minus, we get 405.07. We can be 95% confident that the mean loss of all pickpocket offenses is somewhere between $405.07 and $621.57. We can see that the t-interval procedure and the z-interval procedure are very similar. We just replace the unknown sigma by the sample standard deviation and replace z alpha over 2 by t alpha over 2. Let's look at another example. The data contain a year's chicken consumption in pounds for 17 randomly selected people. Find a 90% confidence interval for the year's mean chicken consumption. The sample size is 17. It is moderate. We need to check the normative assumption using the normal probability plot. The first normal probability plot is constructed using all data. Clearly, there is one outlier. The value is 0. The outlier may be a recording error. It is also possible that this person is a vegetarian and does not eat chicken. We may drop this outlier and claim that our population only contains people who eat chicken. After removing this outlier, we draw the normal probability plot using the remaining data. Now, all points fall roughly on a straight line. It indicates that the normative assumption holds, and we can apply the t-interval procedure. Because one outlier is removed, the sample size now becomes n equals 16. The sample mean is x bar equals 67.125. The sample standard deviation is 11.111. Because we want a 90% confidence interval, alpha equals 0.0. The number of degrees of freedom is n-1 equals 15. Therefore, t alpha over 2 is t.05 equals 1.753. The 90% confidence interval is therefore x bar plus minus t alpha over 2 times s over square root n. Plug in all numbers and the result is 62.256, 71.994. We can be 90% confident that the year's mean chicken assumption among people who eat chicken is somewhere between 62.3 pounds and 72 pounds. The margin of error for a t-interval is t alpha over 2 times s over square root n. The margin of error indicates the accuracy. A small margin of error is always preferred. We have discussed before the relationship between margin of error and confidence level and sample size. Those discussions are still applicable for t-intervals. For fixed sample size, decreasing the confidence level decreases the margin of error and therefore improves the accuracy of a confidence interval estimate. For fixed confidence level, increasing the sample size decreases the margin of error and hence improves the accuracy of a confidence interval estimate.